Yo, so this is one of my favorite number file videos. It's really old. It's 7 years old, but I think I probably watched it for the first time like I don't know 3-ish years ago, and we'll watch the first few seconds.
So it's called the Josephus problem. It's based on something from history. There was a group of Jewish soldiers who were surrounded by the Roman army, and they didn't want to get captured. So they decided to come up with a system to avoid getting captured or suicide. So they'd sit in a circle, and the first man would kill the guy to the left of him. The next remaining living person would kill the next remaining living person with their sword, and they'd go around like this until there's only one person left, and then the last person would have to commit suicide, of course, rather than get captured. And the story, at least the story I was told, I'm not sure this is historically accurate, was that Josephus preferred capture to suicide, but he worried that if he said this, the other soldiers would turn on it. And so he wanted to figure out where should he sit within this circle in order to be the last man living.
So that's the premise. A little morbid, but like that's the premise. So the Josephus problem then is really okay. Where does he stand in the original story? There's a group of 41, but so you could generalize that out to any number. We've got 11 bubbles here, so this is n of 11. And if we were asking where should you stand to stay alive in this one, so then we've got one gets two, this one gets that one, this one gets that one, etc. So you should stand at 7. So when I first heard the problem, you watch the rest of the video, and there is a mathematical way to generalize this problem. So there is a constant time solution to this. But I'm not very good at math. I like math, but I'm not very good at it. So when I saw the video, I thought to myself, oh, okay, cool. Well, how could I solve that? And I made a solution using Python lists, and it was ugly, super ugly. I had probably really just started writing code, and so it was really nasty. And I did use a Python list. The problem is, if you think about a Python list, you have basically this ordered sequence of boxes that you can store stuff in memory, right? And they're labeled. So you can do really efficient lookups. You can look up, what's in box number 4? Well, go to that spot in memory where 4 is and read whatever's in that box. The issue, though, is you can think about the fact that we had 11 bubbles here before, and that we had to pop them in sequence over and over again. And so if you do a pop, you actually have to shift over these boxes, right? So you have to relabel these different boxes. So if you were to pop the 4th element off the list, or the element at index 4, because it's 0 indexed, you have to go through and iteratively, for anything beyond that index, relabel it. And so that could be, the worst case there is you pop the front, right? There are decks or double-ended queues that Python has, which would make popping from the front and popping from the ends easy, right? Because you don't actually have to shift anything over. You literally just delete the end, right? But in the worst case, you have to pop the front, and so then that becomes, you have to shift literally everything else over. Decks handle this side and this side to make those efficient. But in this problem, you're really doing every other one. And so you can imagine there's a lot of index shifting that you'd have to do. So a solution, now my original solution that I did a few years ago, I still used Python list, even though, I didn't recognize that would be maybe a performance issue. But so another way you could go about it is using a linked list. And so a list node, depending on your implementation, if you're making a singly linked list, you'd have nodes that have data and next. So then they just kind of point off to the immediate next element in your linked list. You can have a doubly linked list where each node has a previous and it's pointing back to something. But if you want to pop something out of a list, let's say we want to pop the fifth element off this list, that's this one, then we need to go to it. In this case, we do have to still iterate to here, but we won't have to do the shifting that we had to do before, because we can literally just go, when we go, okay, this is the one that I want, I'm going to grab this here. This one is my previous. Well, actually, better yet, let's do this with the doubly, because you have to look back, right? So if you say, I want to delete the fifth thing, you would pull this down, and you'd say, okay, what am I pointing at, right? So I'm looking at this one. Well, what is previous to me, right? Well, that's this one. So why don't we just make the pointer to this one point there, and we'll make the pointer to the next one, whoopsies, point to the previous, right? And then I can just get rid of this. And this gets deallocated kind of spookily. It just like sort of disappears, right? There's no reference to it anymore. And so now you don't have to do any like shifting down here at the later end. The thing is, in either of these cases, like, you know, for the Josephus problem, we not only have like we have a one-dimensional shape, right? We have a one-dimensional shape. It is a circle, but it's cyclical, right? It goes back around and around and around again. And so this go round, what I told myself was, well, why don't I make my own class? I'll make a circle list, and I will see how that performs compared to a Python list. My curiosity had to do with how inefficient was this particular part, the shifting of the indexes after a pop that's in the middle, right? And those are going to happen a lot, right? Because, you know, they get shifted frequently. Literally every other step you're doing these shifts. And so I thought it was probably pretty inefficient. So I came up with this circle list data structure. And the circle list actually only has a few members. It has head and it has tail. And so head points at the first list node. That one points, and actually all of these list nodes, I am using a doubly linked. So all of these list nodes actually do have pointers back to their previous as well. This drawing's getting rough, but so this one points forward to list node 2, forward to list node 3, forward to list node 4. And so you can imagine you start at 1 and you want to delete 2. So all I have to do is point this pointer here, and this pointer, this pointer there, and then this guy's free, right? I can get rid of this guy. And you just follow that pattern. We're now this guy's turn. This one then gets deleted. And pointers, it's basically just like pointer shifting, right? But so then 4 would go away. And so tail would then have to get reassigned to 3, right? So why don't we go ahead? I'll just kind of show off the whole thing, right? It's time to get rid of 4. So where does 4 point? Oh, well, 4 points to 1. So then we will make 3 point to 1. And what points back to 4? Oh, well, that's also 1. So we'll just make these pointers point at one another. Get rid of this one. And so now you can see pointer to tail is off in nothing land. So we do also need to go ahead and reassign that there. But now it's 1's turn, and 3 gets deallocated. And importantly, this tail also then gets pointed back at node 1. And the next points back to 1 as well as previous. So it is extremely self-referential. But so this was the structure that I thought could maybe work okay, because you're not doing any of the crazy index shifting that you would have to do with a Python list. You're in some sense, maybe only, doing half of the work. You get to the node that you want to delete, and then you don't have to do that shifting, right? So in some sense, maybe you're doing about half of the work. That was my thought. Before we get into that, though, well, actually, maybe we'll show the thing off. So this is my implementation here, and so effectively we've got our class, all of our methods for said circle list class. I really need to put in some more notation down here for these other methods, just so that they make a little more sense. But it behaves very much like you might expect. So why don't we do this? We will go ahead and we will do Python 3. And there we go. From circle list, import circle list, just to show off this, right? So this is actually, I put this in takeaways here. So you could imagine that I'm doing this in a brand new file. And as far as a REPL is concerned, it might as well be a new context, right? I just got output, right? I imported something, but I got output. And if we look at circlelist.py, you'll notice that this was just a thing that I wanted to highlight as a takeaway. I knew about this, but I had forgotten. Any function call that is in some module that you want to import is going to get run when you import it. The whole file, in some sense, gets run when you import it. There's maybe some interesting, like, weird footguns. If you're doing, like, singleton things, and maybe, like, you're just wanting to have, like, keep track of all the instances of a certain thing. If you accidentally make one in your module, then when you import it, you already have one. And when you don't expect that you should have one. So I just wanted to show that off here. But so we'll get rid of that line, save that. But so we'll go back to here. Yeah. So we've imported circle list. So then circle equals circle list. So we'll initialize this. Init. Oh, okay. Interestingly, I don't know why in the REPL it's creating an error there, but so you should be able to initialize the circle list actually without data, but we'll go ahead and we'll initialize it with some data. Circle equals circle list. And basically the way I did this was so that, there we go. So when I did this, I made it such that you could pass in an iterable when you initialize, and then it's just going to populate your circle for you. So if we say circle here, you'll see list node data 1, and then it's going to go backwards, right? And you'll see it kind of counts backwards, so then it goes 2, okay, 3, 4, and it shows off, kind of the structure, and it is very self-referential. This is kind of gnarly to look at. But that's kind of how the thing is shaped. So from there, so value equals circle.pop. If we don't specify here, then we can see that value is just going to be the last thing in the list. And then if we look at circle again, then it is one element less. Not made apparent here by the actual output, but so from there, we can also pop the head of the list. So if we want to say circle dot pop 0, then we can get rid of the head, and now we have 2, 3, right? Tails 3, and then you can see, okay, there's only 2 things left in here, but then we can add things back to the end. So circle dot append 100. And so it just behaves the way you might expect. And then we can say for node in circle, we will print node.data. And we can do that. And here we are. We're in our cycle, right? So you can see it's cyclical, right? Because it is self-referential, and so you can see we go 2, 3, 100 over and over again. And so this is kind of how it works in practice. And so let's go to the takeaways because one thing I didn't know. This is just a couple little things that I found interesting. So if we go over to main.py now, we hop down into the main function. This is gnarly. There's a whole bunch of functions here. I don't know what those functions are. And so I don't know what those functions are. So and in Neovim, I'm still learning a lot about Neovim. But so I did not know that you could hover over a function and you could hit Shift K and then you get the documentation for that function. And this is super handy. I did not know that this was a thing. We'll note here, like, there's basically what I have done is I have a whole bunch of different kind of implementations to solve the Josephus problem. If you watch the video to the end, like I mentioned before, there's a mathematical way to do that. There's an even kind of neater way to do it with the binary, where you take the most significant bit and you basically just slap it on the end, convert it back to an int, and you have your answer. Super cool. But so anyways, this is kind of the idea. From here, I'm going to actually run this. And so we can go back out here. So if we run Python 3 main.py, what we do first, if I hadn't gotten rid of that print statement at the end of circle list, it would still be populating here, because when we import into main.py, we then run the entirety of whatever we import, right? But so I didn't put any inputs. We have this nice little doc string here to tell us how to use it. This is kind of neat. I really liked this. So functions, when you make them, if you put doc strings here, they're going to get stored in the docdunder field for your function. And so you can just write your stuff here. And then if it like for some reason the user doesn't use your thing the way you expect them to or want them to, you can actually raise and exit and just give them the docs. Super nice. But so basically, okay, well, let's figure out the actual Josephus problem. So if we do Python 3 main.py, we'll do 41 because that's the actual Josephus problem. The answer should be 19. And here we are. So 19, 19, 19, 19, 19. Beautiful. Progressively longer and longer execution times. Something that's weird, though. You see the args. We have 41, 41, 41, 41. And then we have the args here, which is our circle list, which is what we expect. That's what we're passing into circle remove next, because we've already populated a circle and then passed it in as an argument to this function. But the head is at data.3. That's kind of weird. Why is that? We don't know. This is like a weird, sneaky footgun where with lists and I believe a few other data types in Python, you get passed by reference. And so this is the decorator that's actually creating the output, right? So I made this timer decorator. You want to see what it does? Well, let's just Shift K. It's a decorator function that provides execution diagnostics in nanoseconds for passed-in function. So basically, it measures how long something takes to execute. So what I do at the start in the kind of wrapped function here is I get the function name, I get its arguments, its keyword arguments, and then basically we do the function and we just time it, right? And then we actually display the diagnostics. We return the actual output of the function. That's what's happening in this inner function here. And so, interestingly, though, you would think, well, list args, because args are structured as a tuple. Args are a tuple, and I believe keyword args are a dict. So this, when you do this copy here. You convert. I'm converting into a list so it looks nicer to my eyes, which is stupid, but I do it anyways. You know, thought that, you know, okay, cool. Now this thing owns args, right? And so then when I print down here, function args, my expectation is that the state of this should remain the same. But because it's passed by reference, and for the case of the circle remove next function, it's actually mutating the state of the circle. And so the arg is the circle. And so when we have it here, because it is a pass by reference, if it gets mutated here at the actual function execution, it's also changing my function args here. And so you might think to yourself, as I did, that, okay, cool, well, I'll just make a copy of it, right? And we'll note we do the same thing. Let's just do what we did a second ago, bop. We still have this issue, data 3, data 41. And so I should also note circle remove next and build circle remove next. There's something wrong with my logic, specifically in the remove next method for the circle. But neither here nor there. It works on the small numbers, and for some reason when the numbers get big, it breaks. So don't know why. I'll figure it out. But so this actually doesn't even work because this copy is not a deep copy. It does not. It is not going to allocate new space on the heap for a kind of a container style object like this. And so what you actually have to do is you have to come in and you have to make a literal deep copy of that data structure. And we can do the same thing here. Deep copy list items. That one should be okay. Cool. There we go. Delete to the end of line. Cool. Right. Where did my start go? Undo. There we go. Okay. Whoops. Delete to the end of line. Okay. So there we are. So this is that. So now actually to look at the execution. So unsurprisingly, binary Josephus, which literally takes the number, converts it to binary, takes the most significant bit, puts it on the end, converts it back to an integer, spits it out. Super fast. Incredibly fast. This, to me, was a little shocking. Where List Josephus it takes very little time compared to the circle list that I implemented myself. And so I wanted to see, okay, cool, like what's going on here? Why is this so much faster than my implementation? I should show off. So now that we have deep copy, let's do that again. And so then you can see, here's our one, go way down, two's down here somewhere. One moment. Okay, so had some family show up to hang out with us for the weekend. So I don't remember exactly where I was. Let's see. I think what I had just shown was in order to actually get a legitimate copy of like a pass by reference object in Python, you actually have to do a deep copy. So you have to tell the Python interpreter, okay, this particular object, go get all of it, allocate new memory on the heap for me, and stick that new thing there so that I have an actual copy of the thing. So then if we actually look at the performance here, non-surprisingly, the binary one is easy. It's super fast. It's basically a couple type conversions and a string concatenation. Super fast. The list Josephus, if you look at it, and we talked about it kind of at the start, like you would assume that with a whole bunch of like in the middle of the list pops and all of the index shifting that you would have to do, that it would be pretty inefficient. But if you look at the circle implementations. So what I want to point out is I have 3 different versions of this thing. So this one is the one that if I had to say, okay, hey, this is like what a normal person would write. It is the build circle remove, which is this one right here. So basically we get a number, we're going to build that circle. And so basically we're using the built-in extend method that I implemented for circle list. So it's going to build that circle. We're going to grab the first element. So we're going to get the head. And then basically we're just going to remove the next, iteratively remove the next node until there's only one node left. And then you're going to return that node's data. So like a sane person would probably write it this way. I had tested it and it was slow, like really slow. If you look at it comparatively, it's worse than 10 times slower than the list implementation. So then I was like, okay, well, my remove function is kind of bad because remove for any non-head or tail removal, you have to start at the front. And then basically while you're not at the node that you want to be at, you're iterating. So if we go back here, it's basically, okay, every single time we're starting at head and we have to iterate across until we find the one that we want to delete, grab that one, pointer shift, and then go again. And so you're still doing a lot of iteration on the remove. So then I made remove next. And so it uses this kind of, I thought, okay, cool, this will be a private field. And so I'll underscore it, this cur member of the circle list. And the thing is, the way I've implemented remove next, you would still have to actually use it. You would use what should be a private field publicly. So that's not really what you want to do. But so in the case of the circle remove next, you're still, build circle remove next. You're still building the circle like you would do here, right? And then you are removing the next one. And so I made the cur member of the circle list class so that really exclusively for this purpose, right, is that you're reducing down to a single element. And so what I could do is I could make this one private. I could make that a private method that gets used in a public method reduce. And so then reduce would do what is inside the body of this build circle remove next is you make the circle while it's greater than 1, just call the private remove next over and over again. Ultimately, take cur.data and return that thing, right? So you could make a public method for this private method remove next. I think that's kind of the most logical way to go about it. But even you look at that one, you're building the list. Let's see, build the list and remove next. It's 53,000 nanoseconds. We have 9,000 here. So you're talking about 6-ish times slower than the list. So then I was like, okay, well, we'll do better. We won't even build the circle in the function. That's where circle remove next came from, which is right here. So you're getting the circle as the input. That's what we're looking at here. And then you are iteratively removing. And so here's the moral is even this 46,000 nanoseconds, many multiples slower than the list implementation. And so you might think, well, if we're looking at that from an O of N perspective, we're thinking about it algorithmically, it should be faster, right? But here's the thing. My circle list is implemented in Python. Python lists in C Python are implemented in C. And the Python interpreter has all of these smart ways of optimizing your code as it gets lowered down into machine code. And that is ultimately like why the list is infinitely faster than my circle list. If I were to go implement circle list in C or Zig or Rust or Go or insert other faster lower level system language, it would be a hell of a lot faster than it is implemented in Python. So then the question is like, well, then when or why would you actually build your own data structure? Why would you build your own class? And I think it all comes down to behavior, right? Like if you're computing a single value, firstly, if you're computing a single value and it can be expressed as math or as some kind of binary operation, like if you think hard enough about the problem, you can probably find an extremely, there's going to be constraints, right? It's like you might be getting a whole bunch of data and slapping it into a list, and then you need to sort it and then search it. Like there are, depending on your use case, there's going to be constraints that you can't get around. In the case of the Josephus problem, it can be expressed as math. You can just do some math. You're going to figure out the thing, and you can do it in constant time. In the case of the binary Josephus, the way I've done it, the binary is going to get longer. So then, you're getting slightly slower as you go along. So it's not technically constant time. But you could implement this as just a math function and it would be legit constant. It would be basically the same runtime regardless of your in. And so obviously list Josephus, circle remove next, build circle remove next, and circle remove, build circle remove. All of these are utilizing memory, so you're getting Alex and D-Alex that you wouldn't even have in like a math operation. So the thing is, like, maybe you can't, you're in a position where at the moment you just need a fast solution. You need to build something quickly, and you frame it and using memory, and you get something that gives you the right answer. Like, that's great, fabulous. Getting the answer is the most important thing. Getting it right is even more important. But like, the question then is like, okay, and this is it, I'm backtracking here. If you can use a built-in in Python, should you ever bother building some custom data structure, building some custom class? I think, like, if you're doing something that's computational like this, it doesn't make a ton of sense. But if you look at the circle list, you can imagine a bunch of different possible utilities for this. Let's go back and see if we can kind of like Control Z our way back to our list. We're gonna get there. Okay, here we are. Imagine a turn-based game, right? You have a turn-based game and you have this cyclical list. The game is just going to continue until somebody wins. This is a really good data structure for that. You can just pass around whoever's turn it is. There's a bunch of cool ways that you could go about doing it. And so the thing is, like the circle list in this, for the Josephus problem, not efficient. No surprise, you're building in Python versus C. And so no surprise, it's slow. But if you have something like in the case of a list, you could implement that. Like, you could implement a game and use a list, and because it's in C, it's going to be faster. But the thing is, like, you can imagine a world where building that with a list, like, might get gnarly to think about, thinking about it as a list. Where with the circle list, you could imagine, okay, it's turn-based. You can build your abstraction in a way that is more easy to grok when you come back and you revisit your code, and you make edits to your game or your turn-based workflow or whatever, right? And so that's just some stuff that basically I came away from, like, go ahead, like, building this thing. Also, like, honestly, just a good opportunity to, like, build your own data structure, think about it. There were some really interesting problems that I encountered as I was building this, where at the very beginning, when I was adding nodes, it was like backwards. It was like 1, 41, 40, 39, 38, right, all the way to 2. And there was some interesting, like, basically pointer swapping that I had backwards. And so there's value to building these things. I think, like, if you are looking for something that's high performance, and you want it to be super duper fast, then, like, implementing it in Python probably isn't what you want to do. I'm going to be exploring Mojo in the coming months. It effectively gives you the ability to, like, unroll loops with just a decorator. That's crazy. You're telling your compiler, just take this for loop that's 100 iterations long and make it 100 different things. That's nuts. It's crazy. So anyways, that's what I've been working on over the past couple days. It was really fun to do regardless. Also really trying to, like, sort of take my medicine and write my doc strings and write my comments and my inline comments and stuff. It's, I'm getting there slowly. But hopefully this was a fun video to watch. And if you think of other crap that you would want to hear about, tell me. Peace.